Yes, so good afternoon, everyone. Our group is tasked with doing polar coordinates and some of the equations with respect to that the polar coordinates, some of the equations that we're looking at. So that's a brief synopsis of what we'll be doing. First, we'll define what polar coordinates refer to. So let's go ahead with that. So very brief definition here for polar coordinates. See that when each point on a plane of two-dimensional coordinate system is decided by a distance from a reference point and an angle taken from a reference direction, it is known as the polar coordinate system. So the pole is the reference point, polar axis, that is the line segment ray from the pole in the reference direction in the polar coordinate system, and the origin is called pole. So um, we have a diagram here that demonstrates what I'm talking about. So here would be the pole. The polar axis would be this point here that radiates outward from the pole. And it will have some displacement theta from the positive x-axis, which will be here, right? So in a normal Cartesian equation or normal Cartesian coordinate system, you would write the point as xy. But in this polar coordinate system, you're writing it as the distance the point is from the reference point, which is r, and the angle of displacement at which this polar axis lies, which is theta. And it's always measured from the positive x-axis, you know, going this way. That's going to be anti-clockwise. So this here is the polar coordinates, basically, where you have r, which is pretty much the hypotenuse of a triangle if you look carefully, and then you have theta, the displacement, the angle at which the polar axis is being displaced on the pole, or from the x-axis rather. So the r that you just see can be negative, it can also be positive. Um, the value of the angles can change based on which quadrant this polar axis lies in. So the polar axis is in the first quadrant, then it's just a normal factor of the value that you can use. If it's in the second quadrant, you're gonna have to add pi. Same goes for the other quadrants. This is radians, so it's gonna be 180 degrees like you're at it. So we have a graph below here, table rather, and a diagram showing what's happening here. So we know based on our previous knowledge that in the first quadrant, that's going to give us range of angles from 0 to 90 degrees. The second quadrant is going to give us from 90 to 180 degrees. The third quadrant is going to be 180 degrees to 70, while the fourth quadrant here is going to be to 70 degrees. And you can see the way the x and y values are negative and positive. So yeah, y is positive in the second quadrant, x is negative, and etc. This here is a diagrammatic representation of the polar grid. As you can see, this here is going to be the pole. These are several polar axes, see, radiating outwards, and they have the various angles at which they are at. Again, this here is the pole, sorry, and the line that is radiating outwards is going to be the polar axis, right? And the displacement here is going to be theta, where is displacement on the x-axis, positive x-axis. Good. So let's look at some definitions here. So we can write an infinite number of polar coordinates for one coordinate point. I'm gonna go more into that so you can see what I'm talking about. So using the formula, you have r, and theta could be plus 2 pi n, or it could be minus r, and theta could be plus 2 n plus 1 times pi, where n is an integer. The value of theta is positive if measured counterclockwise, which is this way, right? This is going to be positively measured counterclockwise. The value of theta is going to be negative we can measure clockwise, which is this way, right? The value of r is positive if laid off at terminal side of theta. So whenever r, as you can see in the diagram here, this is the terminal side of theta. Whenever r is present in this way, it's always positive. R is always going to be positive. The value of r is negative if laid off at the prolongation to the origin from the terminal side of theta. So r is going to be negative if we actually prolong it to the origin, right? So r here is negative. This is basically just adding 180 degrees. It achieves the same thing, right? So you can either add 180 degrees, r is going to be negative, or you could prolong it. Just draw something, well, pass it through the origin here, the pole, and you would have a negative r in the opposite direction, right? That's basically what this statement here is trying to tell us. So what this means, just like also was brought up on here, on top here, is that we can have multiple representations for, um, for, for example, for one, polar coordinate. And then we're going to work some examples of that so you can see what I'm talking about. Because of this fact, you can have multiple different representation of the same polar coordinate. So on this graph, you can clearly see that x is going to be equal to r cos theta here, and y is going to be equal to r sin theta. Both r is the hypotenuse and the displacement angle here is theta. So x squared plus y squared, we could easily form an expression here where you get r cos theta squared is equal to r cos theta squared plus r sin theta squared, right? And that can simplify to give us this expression here. Where you clearly see is Pythagoras theorem, where r is equal to the root of the sum of x squared plus y squared, right? So that's a simple way to figure out find for r. We can simply find the angle of displacement by using the trigonometric ratio, which is tan inverse of y upon x, and you would get the angle here. So basically, these are the static equations or expressions that you would need to know to convert or, well, to operate with polar coordinates. So the examples that we're going to go through is going to be using these equations, relatively simple equations that you should know about. So the first example here, example one, wants us to convert the polar coordinate 4 and 5 and 2 to rectangular points. So the rectangular or the Cartesian points or Cartesian coordinates is pretty much the same thing. So what they're asking us to do is to convert this polar coordinate to Cartesian coordinates or rectangular coordinates or rectangular points. So we know that x, that's how we want to find the rectangular points or the Cartesian coordinates xy. We know that x is going to be equal to r cos theta and y is going to be equal to r sin theta. From the expression here, we know that 4 is going to be r and the angle theta is going to be pi upon 2, which is basically equal to what was radians actually. So it's going to be negative, right? So we just plug those values in. X will be 4 cos 5 on 2, make sure it's well, calculated in radians or degrees. Use degrees here, and you would have x being 0. Do the same thing here, and y is going to be 4. So our points is going to be just 0, 4. For example number 2, they want us to convert the rectangular or Cartesian coordinates to polar coordinates. We know that polar coordinates are r and theta. So basically, we need to find the hypotenuse and the angle. So we can simply do that by using Pythagoras theorem, putting the values, and you'll have pi, the root of 8. Sorry, and you rationalize that, you'll have 2 root 2. You do the same thing here. You plug in information, use trigonometric return, and you find the common inverse. You're going to have pi upon 4. This is in radians, of course. So again, r, well, you're going to have your Cartesian coordinates as you can see here, 2 root 2 and pi upon 4. Those, that is an answer to this question. But r could be a positive number, right? Remember, it could be qualified in anything is actually plus or minus, and there are infinite amount of angles that you can get because the cos and the sine curve, there are continuous curves that go on forever, so you can have infinite amount of angles that you can actually pair it for, right? You can have other representation of your answer. So you could see some of the representations here given. It's going to be 2 root 2 pi upon 4. You can have minus 2 root 2 pi upon 4. You can have 2 root 2 minus 7 pi upon 4. Right? So these are also all possible coordinates of the Cartesian points to 2. Okay. These are the two examples that I have, but I want to go through some other examples with you that I didn't include in the PowerPoints. But see, for example, a question came like you have x squared plus 2y squared is equal to 6. Now this is a coordinate equation. And I want you to express this coordinate equation in, let's say, polar equation, right? Find a polar coordinate equation for this. So again, you could use this here. This is going to be the equation used for the coordinates, and this is going to be, well, the Cartesian coordinates, and this is going to be the equation used for the polar coordinates. So you can just simply substitute x here, where x is equal to r cos theta, and the y here, where y is equal to r sine theta, and you just simply simplify it. All right, so that's going to be r r cos theta squared plus 2 r sine theta squared. That's going to be equal to 6. So you just simplify here, you find the common denominator, you're gonna, sorry, the factorize it, and you're gonna have you're gonna end up with r squared, right? And you get this as your polar equation. A next example, say for example, they give you, say for example, you have the polar equation r is equal to 8 cos theta, and I want you to translate this or transform it into the rectangular coordinate equation. So what can we do? Well, we know that r, right? R here, right here is equal to this. So whenever we see r here, we could just simply substitute it. So we're gonna have root of x squared plus y squared is equal, and by the way, it's cos theta is gonna equal to, you look here, so the x is equal to r cos theta. Cos theta is basically just exponent, right? We can rewrite it in this form and put it in here as well, right? So we're gonna have the root of x squared plus y squared is equal to 8x upon r. And we already know what r is. R is the root of the sum of x squared plus y squared. So we can rewrite that like this. We can do some simple algebra down here, and the expression will simplify to x squared minus 8x plus y equals 0. So we have written the polar coordinate equation in Cartesian equation, right? So those are questions that you can actually come for an exam, or you can be examined on, along with converting um simple Cartesian points to polar points, or polar points to Cartesian points. So I'm gonna hand over to my next colleague who's gonna talk about graphs of polar equations. Just before I do that, I just want to talk about what are graphs of polar equations. Like I just said, for any equation R is equal to f of theta, the graph of this equation, right, for any points that satisfy R and theta is basically what we call the polar graph or the polar equation. So we're gonna discuss two of these graphs, and we're gonna take you through that.
Good afternoon, everyone. I will be talking about the rose scarf. As Jared said, we will be talking about two of those. The first one is the rose scarf. The rose scarf is a popular graph of the form, or that's the equation it's normally being recognized in. R is equal to A cos in bracket n theta, or R is equal to A sine in bracket n theta, where A is the length of the petal. Well, we're talking about a rose, right? From the name, we could know that it will shape like a rose which has petals. And N determines the number of petals. Let me tell you what each of those letters are signify in the form that the rose curve normally takes. R represents the distance from the origin or the pole to a point on the curve. The A determines the length of each petal, and cos or sine, those two trigonometric functions create the shape of the rose curve. And if n is odd, the curve will have n petals. And if n is even, the curve will have 2n petals. So any even curve, the number 2 will be in front. N signifies the number of petals. So odd, you just have the number of petals. But if the petal is even, they have 2 and then the number they have. So, for example, the equation R is equal to 2 cos 3 theta represent a 3-petal rose curve, and R 2 sine 4 theta represent a 4 rose curve. If you see there from the equation, we substitute 3 and 4 where in the original equation there is n. Good. The first example I would like to take you through is sketch the graph of R is equal to 2 cos 4 theta. So the solution, we're testing for symmetry. We find again that the symmetry tests do not tell the whole story. The graph is not symmetric with respect to the polar axis, but also with respect to the line. Theta is equal to pi over 2 and the 4. Now, first thing we do is we find the zeros and we make the substitution u is equal to 4 theta. Substituting 0 is equal to 2 cos 4 theta. 0 is equal to cos 4 theta. 0 is equal to cos u. And when we carry over, we have cos to the negative 1 power 0 is equal to u. Hence, u will be equal to theta over pi over 2, sorry. And 4 theta is equal to pi over 2. So our final value there, or our final answer for theta will be pi over 8. Zero is equal to theta is equal to pi over 8. So the point 0 and pi over 8 is on the curve. And next we find the maximum, which is r, and we know that the maximum value of cos u is equal to 1 when theta is equal to 0. So r is equal to 2 cos 4 0. So 4 times 0, sorry. So r is equal to 2 cos 0, and substitute, our final answer will be r is equal to 2. So the point 20 is on the curve. So next below I have the table where you will substitute to have the various points of the value for theta and the value for r. You can see there we have when theta is equal to 0, r is equal to 2. When theta is equal to pi over 8, r is equal to 0. When theta is equal to pi over 4, r is equal to negative 2. When it's equal to 3 over pi, 3 pi, sorry, over 8, r is equal to 0. When theta is equal to pi over 2, r is equal to 2. When it's equal to 5 pi theta, 5 pi 8, r is equal to 0. And finally, when theta is equal to 3 pi 4, r is equal to negative. When you see it on the graph itself, it will be a little bit more clear. We have a graph. So you can see on the graph here that r is equal to 0 when theta is equal to pi over 8. It makes sense to divide values in the table by pi over 8 units. A definite pattern emerge. Look at the ranges of r values that's on the table. 2, 0, negative 2, 0, and so on. This represents the development of a curve one petal at a time. Starting at r is equal to 0, each petal extends out at a distance of r is equal to 2 and then turns back, if you can see on the diagram here, and then it turns back to 0 and times for the total of 8 petals. So from the graph here, you can see that this have 8 petals here. That's our first example on the rose curve. Next, we have our next example of we're sketching the graph of r is equal to 2 sine 5 in brackets 5 theta. The graph of the equation shows symmetry with respect to the line. Theta is equal to pi over 2. Next, we find the 0 and maximum value as we did, and we will make the substitution of u is equal to 5 theta. So, as we did earlier, 0 is equal to 2 sine in bracket 5 theta. And when we substitute, we have u is equal to 0. So hence, 5 theta is equal to 0. And in this case here, theta is equal to 0. Now, to find the maximum value when sine theta is the maximum. Therefore, r is equal to 2 sine, open bracket, 5 times pi over 2. And we have there that r is equal to 0 when we substitute when we work the equation here. So we have our table again and our graph. So the maximum value of the polar equation is 2. This is the length of each petal. As the curve for end odd yields or the same number of petals as n, there will be 5 petals on the graph. So looking at our table, we have the values for theta and for r here. When theta is equal to 0, we will have r is equal to 0 as well. Then when theta is equal to pi over 6, r is equal to 1. And theta is equal to pi over 3, r is equal to negative 1.73. When theta is equal to pi over 2, r is equal to 0. And the next one, theta is equal to 2 pi over 3. R is equal to negative 1.73. When theta is equal to 5 pi over 6, R is 1. And finally, when theta is equal to pi, R is equal to 0. You can see on the diagram there, the part that shows A. And we have the turning point, as we find earlier, we had the maximum value is 2. And if you can see, as the petal go out to 2, it comes back. So basically, that is our turning point. That's our we did 2 example on the rose curve. I hope that was clear. I will now hand you over to our next colleague who will take you through the next polar so that we will be looking at.
Good afternoon, everyone. I'll be taking you through the lemniscate. And on our first slide for this lemniscate here, we have the definition. What is lemniscate? In geometry, the lemniscate is a plane curve defined from 2 given points, F1 and F2, which is known as the foci, at a distance 2c from each other as the locus of points P. The lemniscate was first described by Jacob Bernoulli as a modification of an ellipse, which is the locus point for which the sum of the distance to each other of the 2 fixed points is a constant. We have a diagram here of what the lemniscate graph looks like. You can see we have the points F1 and F2, and then we have point P. The next slide, please, sir. The properties of the lemniscate curve. The lemniscate is a closed symmetric curve with 2 loops that intersect at 2 points. It has the shape of a mathematical symbol for infinity. The curve is self-intersecting at the origin, forming a figure-8 shape. The lemniscate has 2 axes of symmetry, the x-axis and the y-axis. Thank you. My next colleagues will continue from where I left off.
Good afternoon once again. I'll be looking at graphing the lemniscate function, and so the lemniscate equation is given as the r square is equal to a square cos 2 theta. Now, bear in mind, of all the shapes that we are doing here for polar coordinates, this would be the most unique one because it contains the r square. All the others are singular. This one is squared. So having established that the formula is r square is equal to a square cos 2 theta, it's important to note that there are a few shapes that you would want to remember when you're dealing with lemniscate. As this one here shows you, it's in the horizontal plane, right? So this one here would be r square a square cos 2 theta. When it's in the vertical plane, that means it is vertical. I don't know, sorry, you could see if there's a next slide with the other one. Oh, all right, just hold here. Okay, This one here is where it is having a positive x value, right? It's trending in a diagonal way. As you would know that in that quadrant there, it's positive in the upper right-hand corner there. So there are two others. One is when it is in a vertical position. That one is where it will be, the equation will be r squared is equal to minus a cos 2 theta. No, go back, sir. I don't think that thing is in. And there is another equation when it is pointing towards the left-hand side. If you can picture what I'm saying, as you know, quadrant 1, quadrant 2, right? So it will be in the plane of quadrant 2 and 4 in that position. That was when the equation is going to be r squared is equal to a minus a sine 2 theta. That's right. Correct. Thank you, sir. Right? So this one here would be a sine square or minus a sine 2 theta. Correct. Right? Now, I could now take you now to the graphing of the equation. Next slide. So we have here, graph the polar equation, r squared is equal to 4 sine 2 theta. So we would know that as it is here, r squared, the equation is having r squared here. So we need to make it r. So what we do, we just square root both sides and we will have r is equal to plus or minus the square root of sine or 4 sine square, 4 sine 2 theta rather. And you establish your domain, which you would know, which you would see from the other slide just now, the polar coordinate that is. You establish these points here as shown, right? And you would know from your previous knowledge that these points, these values there, 0, pi over 6, pi over 4, pi over 3, pi over 2, and so on, those would have been the equivalent of the x value. Next slide, please, sir. So here it has been worked out. You do this by using your calculator. Next slide. And this is what, when you put it in the Desmos, this is what you will get, right? It will result in this shape here with the 8 or the bow tie pointing in the positive plane, right? This one here is the one r squared is equal to a sine 2 theta, as we would have just seen in the calculation just now. Next slide, please. Here's another one, and it's very similar. This one here has the cos in it. So what you have noticed is that these equations are not very difficult to remember. They have r squared in front, and it's either sine or cos. And there's a variation between one being negative cos and one being minus sine. So we have chosen to do a positive cos here. And like we have done before, we just find the value of r by square rooting the other side of the right-hand side. And we use our polar coordinates, which is as shown here, 0, pi over 6, pi over 4, 3 pi over 4, 5 pi over 6, and pi. And we will establish our values. Next slide, please. And when we put it in Desmos, this is what you will have. As you notice in this one here, the figure, the lemniscate skate rather, is in the horizontal plane here, which is the x-axis plane. And like I've pointed out earlier, this is when the r squared is having the a cos 2 theta. It's all positive. And if you were to do another one, it would fall under the other side, the other direction. Perhaps if you were to do the vertical axis, it would have been r square is equal to minus a cos 2 theta. But because you should have the idea that you just only have to manipulate the negative or the positive and put it in the calculator there, Desmos, this will be the outcome of it. And so it is important to know that you don't get mixed up. Don't get mixed up at all with it, right? Because it is very easy to recognize. Just recognize the shape. There are four basic shapes or forms that the thing would take. One is in the horizontal position as shown, one in the vertical, one in the positive sloping plane, and one is in the negative sloping plane. There are four such types. That would have bring me to the end of that presentation, and I hand you over to our next colleague, Ms. Rovani.
I don't think Miss Robin is here.
Oh, she's not here?
Because I would have checked the participants and I did that. I didn't see
Oh,
her.
okay, okay. So Miss would have had to present on this. So she would have had to familiarize herself with this part of the presentation. I want
Yeah,
to, yeah. Go ahead, sir.
this course, yeah, I think this course is a pre-calculus course. But in the case we didn't do integration as yet, but to basically get the area inside the region, the loop in the limb scale, you need to use integration. Basically. I think let's just bring through some examples with uh basically doing some integration. So you have so basically you're just finding the integral between 0 and pi, and there's some derivations here that you have to do. Well, you have to do integration, and you would result these expressions here. The area would eventually come out to 2 units. Again, you would need to know how to integrate this part here. Basically, well, the r square basically. So we have r here from the equation, 4 sine 2 theta. So here, so yeah, I think that's what you have to know. But we haven't done calculus yet. So I think this should worry too much about finding the area. We didn't do division yet, so you don't have to worry about finding the area of the landscape. But generally, this is what you would do, right? To find the area of it. And I think any of the curves you intersect the polar equations. So if you have any questions, any questions concerning the two curves and the polar coordinate?